Okay, we're going to start with Isla Simpson, who co-led the Strategic Ensemble Design Task Team, whose remit was to look at which experiments should go in the Assessment Fast Track and the development of that. So I'm going to hand over to Isla now.
All right, thank you. Thanks for the opportunity to present the work of the Strategic Ensemble Design Task Team. So the task team was formed in late 2022. It was co-led by Ben Sanderson and myself, and we had these members listed here, and we had also a number of stakeholders from different kind of sectors that informed things with the task team. And the task of the task team was to inform on the ensemble design of CMIP7. And so there were various things that we discussed, and I'm going to touch on each of these. And we made recommendations to the CMIP panel on how things should look. And this was achieved by discussions among the task team, discussions with the stakeholder group, discussions with MIP leads, discussions with modeling centers, and then there was opportunity for broader input through community surveys and drop-in sessions. And so the first of these is question of 1750 versus 1850 start date. And so this came out of work by the UK GLOSAT project, which recently produced this new gridded temperature data set that goes back to the 1700s. And this group also ran simulations with UK ESM to show the impact of starting at 1750 versus 1850. And so prior to 1850, there are these fairly large volcanic eruptions, and there's some indication from the simulations that could impact the evolution as you go into the late 19th and early 20th century. So the question was, should we actually be starting everything in 1750? And so this was discussed. We decided we couldn't really justify the additional computational expense of that extra 100 years until it had really been shown by more modeling groups that the benefits of doing that really outweighed the computational expense. We also discussed the strategy for emissions-driven simulations. And so we asked the question, how many modeling centers are ready and willing to run with a fully interactive carbon cycle and run with emissions instead of concentrations of carbon? So there's definitely been things done in the past through C4MIP, but it's not been kind of standard to run the CMIP experiments with emissions, and that's obviously the next step up in complexity. And in answer to that question from 25 different modeling groups, about 3/4 of those said that they were ready to do that. And so that led to Ben Sanderson kind of spearheading this effort. He produced this perspective, arguing for the need for emissions-driven simulation so that we could incorporate uncertainties in the carbon cycle more fully into CMIP. And in that effort, he also designed these idealized experiments to characterize the carbon cycle within the model. So these are simulations with flat carbon emissions, or reducing to zero, or going negative to mimic carbon dioxide removal. And so these experiments are going to be part of the fast track. We discussed whether there should be any additions to the deck. And so here's what the CMIP6 deck looked like. And the question is this sufficient to be characterizing the models and provide kind of a base climate assessment for the models? And it was decided that through many discussions that there should be 4 additions to the deck. So one of these, I know there's 5 things here, but these are kind of the same. So the historical is obviously an important way to evaluate the models in their representation of historical climate. And then these 3 RF MIP simulations, they were strongly encouraged in CMIP6, and they are now mandatory in the deck. And these are short time slice experiments that are used for characterizing the model's effective radiative forcing. And then, of course, the big thing for the task team, which is the topic of this session, was the design of the assessment fast track. And so this is a subset of experiments. They're drawn from the community MIPs, and these are being prioritized on this timeline so that they can inform the IPCC. And so we had many discussions of what should be in here, lots of discussions with these kind of mirror board things where we were prioritizing which experiments we thought were most important, and then, of course, surveys also informed on this. And so ultimately, this is the fast track that was decided upon. These include experiments for prediction and projection, and then also for process understanding. And I'll kind of go through each of these different groups of experiments. So first of all, from DCPP, there is an up-to-date initialized prediction, kind of as close as possible to the IPCC deadline to give an initialized prediction for the coming decade. This would most likely be done with a CMIP6 era system because you need the hindcast suite to do de-drifting. And so that will provide an up-to-date initialized prediction. Of course, scenarios are a big part of the IPCC assessment, and so we have these scenarios included. For AirChem MIP, there's a number of experiments. So these experiments listed here, these are future scenarios, but with mitigation of aerosol precursors or aerosol and ozone precursors. And so those will be used to explore the impacts of air quality management in the future on the climate. These experiments from AirChem MIP, these are used to quantify the climate impacts in the historical record of changes in aerosol precursors and aerosol and ozone precursors. And then these experiments here, these are again short time slice experiments where individual forcings are added one at a time. And these are used to produce these kind of figures in the IPCC that quantify the impacts of individual forcings on the climate. For GeoMIP, there's one experiment. This is an experiment under, I think, the medium scenario, but keeping temperatures fixed at 1.5 degrees, I think, using stratospheric aerosol injection, so to explore the impacts of SAI. There's one experiment from PMIP. This is for last interglacial, where you abruptly change the irradiance and the greenhouse gases to be those of 127,000 years ago. And so this gives a warm climate that can be compared with paleo records, particularly useful for looking at situations with a sea ice-free Arctic. For DAMIP, there were 3 experiments that clearly jumped out in the past IPCC report as being the most widely used. Those are the experiments with natural-only forcings, aerosol-only forcings, and greenhouse gas-only forcings. So those are in the fast track, and they're used to produce these kind of figures that attribute historical change to individual forcings. For LMIP, there's an offline land simulation that can be used to characterize the representation of land surface processes under the constraint of observed meteorology. For C4MIP, there are a number of experiments that are used to characterize the radiative and biogeochemical effects of CO2, and also those experiments from Ben's paper that are used to characterize the representation of the carbon cycle in emissions-driven simulations. Of course, the pattern effect is a big topic at the moment, and so there are a number of experiments from CFMIP which can be used to explore that, and also to explore nonlinearities in climate feedbacks under different CO2 levels. And then finally, there's some additional experiments from RFMIP. There's also those ones in the deck, and these are used to quantify the effective radiative forcing of different forcers. The final question that we touched upon was this issue of model preselection. And so the idea here is, could we limit the burden on modeling centers and the carbon footprint of CMIP by pre-selecting models to perform certain experiments? So, of course, as was already mentioned last time, we had this hot model problem where there were a number of models that had high equilibrium climate sensitivities in a way that we thought was probably unrealistic. And so I think there was some weighting done of models after the fact to kind of deal with that. And then also, not all models are independent. There's a common kind of lineage to many of the models. And so maybe we could limit the burden by picking certain models from each different kind of ancestry group to run different experiments. Ultimately, we discussed this and decided not to pursue any model preselection. And so what were the reasons for that? Well, one thing is that it's going to be really difficult to know, only say from the deck ahead of doing all the other experiments, how models are going to perform for all variables that anyone might care about. And I think that's even difficult for global mean temperature. And so for an example here using CSM, CSM2 was a hot model. It had a very high equilibrium climate sensitivity. You can make some relatively small changes to CSM2 and reduce that equilibrium climate sensitivity. But that actually doesn't change the transient climate response. And these 2 different versions of CSM2 look very similar in global mean temperature by the end of 2100. So if you'd ruled out CSM2 because it was a hot model, you might have missed out on any other benefits from having CSM2 in the ensemble. And the fact that it was a hot model actually doesn't have much bearing on the timescales that many people care about. Two models with shared ancestry can exhibit very different behavior. And again, another example from CSM2, it was a hot model. It had an equilibrium climate sensitivity of 5.2. NORI SM2, its atmospheric component is based on the atmosphere of CSM2, and it had one of the lowest equilibrium climate sensitivities. So by picking out models based on their lineage, you might miss out on diversity that would be there in the ensemble. And then finally, it can be useful to have bad models to understand intermodal spread and identify relationships that can be used as emergent constraints. And so overall, it was considered kind of impractical to try to identify models to target for particular experiments ahead of time, and there were concerns that if we did so, we might not span the full uncertainty space with the ensemble. But maybe the rapid evaluation framework can be used to kind of identify gaps in the diversity of models that have performed experiments and kind of target individual models to encourage them to run experiments that may be missing. So to conclude, CMIP7 was designed through many discussions with the task team, the CMIP panel, the MIP and the Modeling Center representatives, and community surveys. An emerging science area for CMIP7 is increased use of emissions-driven simulations, as we'd already heard. And some of the key experiments that are important for characterizing models have moved into the deck, and we now have this assessment fast track that is composed of this subset of experiments from the MIPs that are considered high priority for the IPCC assessment. And then, of course, the other experiments from the MIPs can be done on their own timeline. So thanks for your time, and happy to take any questions.
Thank you very much, Isla. If we've got any questions, please line up at the microphones that are in the aisles there. If we've got any questions online as well, please add them to the Q&A chat. Got a couple of minutes. No? Isla, you were so clear. Oh, we've got one. Please go to the mic.
What would it look like for ESMs to be emissions-driven or process-coupled with respect to the nitrogen cycle?
Yeah, that was I think the next step up in complexity on that diagram from Ben's paper. I don't think many models are doing that at this point, but it's definitely not my area of expertise. I don't know if someone else wants to chime in. Do you want to come up and use this? Or?
Thanks. Yeah, that's a good question. Nicholas Frichard has a poster on that, I think. I can't remember which day that is, but come along. So for nitrogen, it would be activity-driven, so it would be things like applying nitrogen fertilizer that gets into the system and other things like that. But yeah, come to Nicholas' poster.
Okay, we've got one question online as well from Vivek Arora, who asks, what are bad models?
Yeah, no models are bad. Well, I guess what I was especially thinking about is you might have a model that's really biased in some feature of the climate system, and that bias could impact how it responds, but you don't really get to know that unless you have those bad models to see the relationship between present-day climate issues and how the model changes.
Great. Thank you very much, Isla.